Hello, welcome. So today what I'd like to do is talk about a topic we haven't really talked about, although it's come up a few times, because it gives us an opportunity to review a whole lot of things, especially things from the beginning of the course that we haven't talked about for kind of a long time. And it's sort of a cool topic anyway. The topic is sparks. And sparks in air is a topic that encompasses a lot of phenomena. So I think one of you mentioned early on at the beginning of the semester what happened when you shuffle across the floor when in the winter, when it's dry, and then you go reach for a doorknob and you get a shock. Okay, that's a little spark. You may have seen sparks from Van de Graaff generators in demonstrations. You've certainly seen some really big sparks because lightning is sparks writ large. It's a very large, very dramatic spark. And these are all electrical phenomena. And so reviewing, trying to understand, trying to work through, and trying to make models of what happens in a spark gives us a chance to exercise a lot of the ideas that we've developed during the semester. And we'll find that we have to bring in ideas from chapters 13 through 23 to really get it all straight. So let's talk about sparks. I'm going to share my screen here. And let me find the chat window again. Okay. So normally at this point, I would demonstrate a spark with some sort of machine, a Wimshurst machine or something like that. So you can imagine that I've done that, or you can go find your favorite video of lightning strikes online, because that's a good review of a spark. But let's think about a simpler spark for a minute. Let's think about this, what happens when it's winter, you're shuffling across the carpet, you get close to the doorknob, you reach for the doorknob, and you get a spark, a little shock. And you hear it, there's a little crack. And if it's dark, you might even see the light. You can also make sparks by pulling apart sometimes blankets, if it's particularly dry. But there are a lot of questions to answer about sparks. So the first question is, why do we get sparks only when two objects are close together? If this is really an electrical phenomenon, it's electrical current, how does charge move from the doorknob to your finger? Why is a spark short? Why is there light produced? Why do you hear a sound? And we may generate some more questions as we're thinking about this. Well, so Tristan, that's right. So in winter, there's very low humidity, and therefore charge can accumulate more easily on things without being conducted away through water, layers of water, and that's why that can happen. On the other hand, if we get enough charge and a lightning bolt, this can happen even when it's quite humid. But it is true that the low humidity in winter is one of the reasons we can see a spark. Okay, so air may turn into a conductive path, so the charges can flow from the doorknob to the finger. And that's a good guess, but then the question is, how would that happen? How could air become conductive? So that generates that guess generates a new question, doesn't it? Why a particular elevator shocks you up time you press the up button? I'm guessing something isn't appropriately grounded. But so that's that, but it's still a spark, right? So charge has accumulated somewhere because it should have trickled off into the ground, but hasn't. Okay, so the air ionizes. So how can air be? How can we ionize air? Okay, when there's a high enough electric field, so why? So we know that the the critical electric field, is about 3 times 10 to the 6th newtons per coulomb. That's the field we need before we can get a spark in air, before air ionizes. There's a suggestion that we need a big field, and so we need a big field. A suggestion that we need to think about potential difference. That's a good guess. And somebody's talking about polarization and the finger and the doorknob polarizing each other, and that's going to be important too. So you kind of make a capacitor, make a dipole or something like that. So those are great suggestions, and we're going to actually investigate all of them in this discussion. Okay, so we need a big field. So you're all saying we need a big potential difference, we need a big field. That's absolutely right. But the question is, why? What does it do? Okay, so why is a big field important, and what happens? So we have energy also. So we need energy. We might need to think about energy here too. Okay, so let's work through these ideas, sort of one question at a time, and see where we get to. So why is a spark short? Well, so maybe we get to equilibrium somewhere. So equilibrium. Okay. So let's start out by talking about how charge moves through the air. So you've all suggested that air needs to become ionized. It needs to become a conductor. And we know that typically air isn't a conductor. It's an insulator. But couldn't we actually, wouldn't it be possible just for, say, an electron to jump from the doorknob to your finger? So we need to rule out, if nothing else, can an electron jump from doorknob to finger? Okay. And a related issue here is, so we can rephrase this question in sort of physicsy terms by saying, how far can an electron go before it collides with something and doesn't make it? So could it jump from the doorknob to your finger without, on average, colliding with something that stopped it? How far? So how far can an electron go between collisions? And so the physicsy way of thinking about this is to think about what we call the mean free path, where mean actually means average. And what does that mean? It means, on average, how far can a particle travel in air, in a gas, before it collides with something. So I'm going to show a VPython program here. So what is this program? Let me make the window bigger. So this is a gas. This is a model of a gas it's called a hard sphere gas, because when the molecules collide, they just bounce off each other. And all these particles, and this is running in VPython, all these particles are identical. We've just made one of them turquoise, and it's leaving a trail so we can see its path. And you can see the question is, can it get from one wall to the other without changing direction? Because if it changes direction, it's going fast enough that it's hard to see. But if it changes direction in the middle, that means it collided with another particle. And you can see that much of the time, it actually doesn't make it all the way from one wall of the container to the other without a change in direction. So much of the time, there's a collision before it gets from one wall to the next. And so the question is, what is the average distance it goes between this kind of collisions? Now, this program has kind of a small container and not that many molecules, but this is basically the idea that we would use to calculate this. So that is, that's the way we're going to frame this question. And so what we want to do is we want to try to estimate the mean free path. Now, let's think about what the mean free path ought to depend on. So there are various things it could depend on. It could depend on the density of the air. It could depend on how big an air molecule is. Suppose there was a gas that wasn't air, but it had much bigger molecules. Would that make a difference? It could depend on the speed of the particle. So what do you think the factors are that we're going to need to worry about when we're trying to estimate the mean free path of a particle in air? Okay, so most of you are guessing that it depends on everything. So let's think about this. The density makes sense because the more particles we have here, the more likely our particle is to hit one of them when it's trying to go somewhere. It certainly depends on the size of an air molecule, because if these molecules are much bigger, that's certainly going to increase the probability of colliding. Does it depend on the speed of our particle? What the speed tells us is the time between collisions, but not how far it's going to go. So all we care about is distance. So we want distance, not time. So it probably doesn't actually depend on the speed of the particle. So let's try to estimate it. So let's estimate the mean free path in air. And this is a very rough estimate, okay? So here's the idea. If we find the average, the volume of air containing one molecule, on average, and then we say, let's consider this to be a cylinder, because it's just a volume. We could make it a cube, but we could also make it a cylinder. And if we draw this volume of air that contains on average one molecule, and here's our particle of interest. Whoops, here's our particle of interest entering here. Let's say it's an electron. And here is, now, what is the radius of this cylinder? Well, the radius of this cylinder could just sort of be the dimension of a molecule. So if that's N2, that could be the diameter, say, of something like N2. Now, I know it doesn't exactly have a diameter because it's probably shaped like a dumbbell, not a sphere, but roughly some average molecular diameter. And once this electron enters this cylinder, it's guaranteed to collide with one atom. And how far it goes here, the distance it goes before it collides, this is the mean free path. And so that's our unknown. That's the thing we want to solve for. And so if we can find the volume of this cylinder, we can solve for D. If we and estimate the radius, so we can get an approximate. First of all, the volume. So what's the volume? Well, the volume is we want cubic meters per molecule. So we want, we have 22.4 liters per mole at STP, and 1 mole is 6.02 times 10 to the 23rd molecules. And we need to convert to SI units. So 1 liter is a cubic decimeter. So cubic decimeter squared cubic decimeter per liter. And so that's going to give us cubic meters per molecule, per cubic meters per molecule. And when we work that out, we get something like 3.7 times 10 to the minus 26th cubic meters per molecule. And now to solve for D, so we're going to set this equal to the volume of the cylinder. So the volume is equal to, and what's the volume of the cylinder? Well, it's the cross-sectional area times the length, right? So it's pi r squared times D. And we're going to say, let's just say the radius of a typical molecule, or a typical average radius, because the molecule's rotating, is going to be something like 1.5 times 10 to the minus 10 meters. So maybe half of what Tristan's suggesting. Times D, and this is equal, so D is going to be equal to our volume over pi r squared, so it's 3.7 times 10 to the negative 26 cubic meters divided by pi times 1.5 times 10 to the minus 10th meters squared. And we get on the order of 5 times 10 to the negative 7 meters. So this is the mean free path, an estimate. It's not, one can make a more sophisticated estimate if you do statistics, because not all molecules are going the same way and not everything goes one mean free path all the time before a collision. But the bottom line is that a particle in air, like an electron, can only travel about 5 times 10 to the minus 7 meters, so less than a micrometer, before it collides with an air molecule. And so an electron just isn't going to be able to jump from the doorknob to your finger. So no. So no, electron can't jump from knob to finger. However, this mean free path is a useful number that we're going to need later. So so the second question is, suppose air does get ionized. What's going to happen? So let's say 2, if air gets ionized, how does the spark happen? Well, we had a suggestion that, first of all, we obviously are going to need an electric field somewhere. Where is that coming from? So we had a suggestion that there's some polarization going on. So here's our doorknob. Here's you. You are walking across the floor, shuffling your feet on the floor, on the carpet here. And presumably everybody was neutral to start out with. But we know that as you shuffle along, we know that from our experiments with tape that charge can be transferred by contact. So perhaps what's happening is that, say, negative charge, we don't know which way it goes, but let's say negative charge rubs off onto the carpet, leaving a positive charge on the soles of your shoes. But the charge is on your shoes. How does that do anything to the doorknob? So it has to be a little more complicated than that. So let's take it step by step. Now there's positive charge on the soles of your shoes, but your shoe soles are probably insulators. If you're wearing sneakers, they're probably not rubber, they're probably some synthetic, but it's something that's clearly, you're probably not wearing metal-soled shoes. So therefore, it's not just charge traveling through and over your body, but this charge on the soles of your shoes. Yeah, exactly. Shoes are insulators. Those charges won't move. So what charges can move? Where are there charges in you or on you that could move? Absolutely. So the saltwater layer on your body can polarize. And so we would get, the way we've drawn it here, we'd probably get chloride ions more down here, and we'd get sodium ions here. What about the inside of your body? Is there anything that can polarize there? So how about your blood? Are there ions in your blood? Yeah, yeah, absolutely. There are lots of ions in your blood, lots of chloride ions, sodium ions, calcium ions. So in addition to, so we have sweat and blood polarize. And so we end up with an excess of positive charge in and on your hand. Bicarbonate, yep, got some negative ions here too. So maybe we'll make a calcium ion here. And bicarbonate ion down here. Yeah, so there's a lot of ions in our body. But now we have this finger that has an excess of positive charge. When you're far away, not much happens, but as it gets close to the doorknob, which is made of metal, what happens to the doorknob? Well, absolutely, it polarizes, doesn't it? So we're going to have electrons moving to that side of the doorknob, and we're going to have an excess of protons here, a deficiency of negative charge on the other side of the doorknob. And now we start to have an electric field in the space between your finger and the doorknob. And as you get closer and closer, the electric field presumably gets bigger and bigger. Well, it does look like a capacitor, doesn't it? Or a dipole, take your pick. But yes, it looks like a capacitor in a certain sense. We certainly have a positive end and a negative end. And now we have a reason to have an electric field in here. And so if we sort of blow this up, so we draw, here's your finger. Here's the doorknob. So we've got positive charge here, and we've got negative charge here. So if we had ions in the air and we have an electric field, if we had ions in the air, they would absolutely move. So if we had, say, free electrons, they would definitely move that way toward the finger. And if we had positive ions, say if the air had become ionized so that what we had was N2 plus or O2 plus, it would feel a force in the direction of E and move that way. So all of a sudden, we've actually got an electric current here. And so we have a current of electrons flowing toward the finger. We have positively charged ionized N2 or O2 molecules floating toward the doorknob. And is this just going to go on forever, though? I mean, Charles, I think, pointed out equilibrium, or what's going to happen as this charge flows? Well, eventually, that electron or some electron will get to your finger, and it will neutralize some of the positive charge on your finger. And likewise, one of these molecules, these ions, will eventually get here, and it will neutralize some electron. It'll cancel out some of the charge. I mean, it's a quantitative question of how much charge, but it's certainly going to decrease the electric field, right? And eventually, yes. Although, yes. So we get to the point where either the electric field things are completely neutralized and there's zero field, but in any case, the spark stops. So in fact, we're done. So the spark will indeed be short, right? Because eventually the electric field goes to zero. So the spark is short. So why do we see light in this phenomenon? Yep, the charges are accelerating in the field, aren't they? So charges accelerate in the electric field. And so they accelerate, they radiate. Yeah. Okay. So it looks like air ionizing, we like air ionizing. This is a good model. But the question is, how does the air get ionized? Because it isn't always. We're not having sparks all the time. Air really isn't a very good conductor. So what is a process that could explain the ionization of air? We know we need an electric field. Well, let's consider a really simple explanation. So model 1, we'll talk about force. And we'll say that the electric field is large enough to pull an electron out of an atom. Okay. Well, can we estimate how big this field would be? So think for a second about how you might make a rough estimate of how big a field you'd need to pull an electron out of an atom. Yeah, that's a great idea. So the suggestion is, would it be equal to the force that a proton exerts on an electron in orbit, greater and opposite to the force holding the electron to the nucleus? Yeah, absolutely, great idea. So let's make a really simple model of the atom. We'll go back to the Bohr model. Here's our nucleus. Here's an outer electron orbiting at some distance. And even though we know it's not really a circular orbit, it's still and we can think of this as a hydrogen atom, or we could just think of this as any atom where we're taking the nucleus and the inner electrons together to have a charge of plus E, and yeah, okay. So and we'll say the radius of an atom is roughly 10 to the minus 10th meters, which is kind of the radius of a hydrogen atom. And so we say that we make a force argument, and we say that here's our electrons, so that I can do this horizontally. So we say here is the force by the nucleus, and this is the force by the applied field, and they have to be, the force by the applied field has to be just a little bigger than the force by the nucleus. Well, we can estimate this force by the nucleus. Well, we did. So why don't electrons spiral into the nucleus? Well, classically, of course, they would, because they would be accelerated, give off radiation, lose energy, and spiral in. But we barely touched on this in a previous lecture. Quantum mechanically, when an electron is in its ground state and in the lowest radius orbit it can have, there is no lower energy state it could go to. And so there is no mechanism for it to lose energy. So this is very quantum mechanical. Classically, it would. So let's calculate the force in electron fields. So the electric field due to the nucleus. So then we'd have the charge on an electron times the applied field has to be equal to the force on the electron, the field of the nucleus, and we'll just worry about magnitudes here. And so this would mean the applied field would have to be equal or greater than the field of the nucleus. The field due to the nucleus is just 1 over 4 pi epsilon 0 plus E, which is going to be the charge of our nucleus here, over r squared. So that's 9 times 10 to the 9th Newton meters squared per Coulomb squared times 1.6 times 10 to the minus 19 coulombs divided by, what do we say? 1 times 10 to the negative 10 meters squared. And if we work this out, we get a value of 1.4 times 10 to the 11th newtons per coulomb. Now that's an estimate, but we know experimentally that the critical field, the one we need to get a spark, is on the order of 3 times 10 to the 6th newtons per coulomb. So this is a pretty big disagreement. So now what do we do? Do we say, well, we just made a very approximate estimate, we can try to refine the estimate and use better values? Or do we say this discrepancy is so big that this model just can't be right? Well, we're used to being off by factors of 2 or 5, or even an order of magnitude in estimate, but now we're off by 5 orders of magnitude. And that says, no, throw out the model. So we can't, the applied field is absolutely not large enough to pull an electron out of the nucleus. So that's probably not how air is going to become ionized. And this is an important and legitimate way of reasoning physically, the idea that you can rule out a model just by estimating roughly what it should be. So let's say, well, if we can't pull it out, maybe we could knock it out. So model 2, a fast-moving particle can knock out an electron. Yep, that's right. So a fast-moving particle can knock out an electron. Well, where would such a fast-moving particle come from? The answer is invaders from outer space. So what do I mean by invaders from outer space? Well, the Earth is every day, all the time, being bombarded by very energetic particles from outer space. They're usually high energy protons. And very high energy protons. Oh, I was serious. I'm absolutely serious. And so high energy protons, and we're not entirely sure where they all come from, come in and they're doing fine until they hit the atmosphere. So here's our atmosphere. And the atmosphere is made of air, oxygen, nitrogen, ozone, whatever. And because these protons are made of quarks, they interact by the strong force. And so if they get near a molecule, an air molecule, there's a nuclear reaction that goes on. And what we can get from this reaction is we have protons, but we can get neutrons, we can get pi plus and pi minus particles, which are made of 2 quarks. All this stuff interacts by the strong force. We call them hadrons. They're made of quarks called hadrons. They interact with the strong force. And so they don't get very far, because if they start going down toward the Earth, there's a lot of air there, and they just can't go far. So that's not going to help us make a spark on the Earth. There's some other stuff that gets made in these reactions. We get leptons. They don't interact with the strong force. So we get electrons. Electrons are very low mass though, and so they're easily deflected. So they don't really make it very far. But we also get muons, mu plus and mu minus particles. They're like heavy electrons. They're like electrons, but 200 times heavier. Yep, strong force holds protons and neutrons together, but it also holds the quarks together that make up the protons and neutrons. And so anything that's made of quarks can react with any other thing that's made of quarks through the strong force. And so a proton coming near the nucleus of an oxygen atom could react with it and form pions and muons. It also makes neutrinos, but they're not charged. They don't interact except by the weak force, and so they just go right through the Earth and you and everything else. But the muons actually have a shot at getting through. The muons are massive, so they have a lot of momentum. Yeah, it's actually the quarks that are interacting. Muons are made of themselves. So things that are hadrons, like protons and neutrons, are made of quarks. Things that are leptons that are not made of quarks are basically just made of themselves. So an electron just is an electron, and a muon just is a muon, and a neutrino is a neutrino. We don't think they're composed of anything smaller in the current standard model. So what's going to happen here is our muon is going to come down through the air, ionizing things as it goes. We're going to get minus and minus and plus and plus and minus, okay? Because the muon is a charged particle, it interacts through the electric force, so it can knock electrons out fairly easily. So muons ionize air. A little bit. There's a problem with this, though, because muons aren't stable. So a muon, a mu minus, can just decay to an electron and a neutrino and an antineutrino, or a mu plus can decay to a positron and a neutrino and an antineutrino. And the lifetime is about 2 microseconds. So 2 times 10 to the negative 6 seconds. So how far can a muon go far enough to get to the surface of the Earth in 2 microseconds? So how far can it go? In 2 microseconds. Well, okay, it does depend on its speed. So let's put an upper limit. The distance is approximately, we'll say the distance is the speed times the time, of course. So let's say it's less than or equal to the speed of light times 2 times 10 to the minus 6 seconds. So we have 3 times 10 to the 8th meters per second times 2 times 10 to the minus 6 seconds, which gives us 600 meters. It could go less than 600 meters before decaying, but the thickness of the atmosphere is something like 50 kilometers. So that's about, so atmosphere is about 50 times 10 to the third meters. So that can't work, except it does. And why does it work? We get muons coming down through the atmosphere, and it is exactly that. It is a relativistic effect. So time is running slowly because for the muon, which is going fast, because it's going so fast, time runs slowly, and so it doesn't age. So if you remember Alice and Bob and Einstein, where we decided, along with Albert Einstein, that time had to run more slowly in a moving reference frame, for the muon, because in its reference frame, time is passing slowly. So in fact, the muon makes it down to, that's right, in a fast moving reference frame, time runs more slowly. And if the muon is going very fast, close to the speed of light, then in fact, time runs very slowly for the muon. So muons ionize air near the surface. A little bit. Well, is a little ionization enough? And the answer is yes, if we get a chain reaction. How could that happen? Well, let's consider. Here's an N2 molecule. Here's our electric field. Here is one single free electron that was made by being ionized by a muon. And it's obviously going to be going this way. So we start with one free electron. Now what is this electric field? Well, this is the electric field due to your finger in the doorknob here. So without this electric field, nothing happens. But now that we've got this electric field, this electron starts to gain energy. It collides with this N2. And now what we've got is we've got a positive N2 plus. We have our original electron, and we also have a new electron that came off the N2 plus. And we still have this electric field. And so now we have two free electrons. And the field hasn't gone away, so they're both going to go this way. This N2 plus is going to go that way. And after 10 to the minus 7 meters, both of these electrons are going to collide with neutral air molecules. And now what do we have? Well, now we have 3 ionized air molecules, and we've got 4 free electrons. No, the muons don't help with polarization. What the muons do is produce, what the muons give us is the one free electron. But all we needed was that one free electron and our electric field, and now what we get is a chain reaction. So all we needed was that one free electron, and we can get a chain reaction. And the next time we're going to have 8, and then we're going to have 16 and whatnot. So the remaining question is, how big a field do we need to make this happen? And since our force argument didn't help, let's make an energy argument. So we say, if we could figure out the energy required to knock out an electron, then we need to know the kinetic energy of the free electron. That's how much energy it would need. And then we could figure out the potential difference over the mean free path, because that's how far it got to accelerate and gain energy. And so then we could get the electric field required. Okay. So that's the argument here to get this chain reaction. And so basically, here's the energy calculation we need to do. Here's the nucleus and a bound electron. So that's our initial. And in the final state, we've knocked out the electron, so it is extremely far away. This distance, our final, is infinite. And we can say that so this is the potential energy change from the system delta U is E delta V, or minus E delta V in this case. And what's delta V? Well, the potential difference here is V final minus V initial, which is the integral of E dot dl from initial to final. In this case, it's minus the integral of 1 over 4 pi epsilon 0 E over x squared dx, because the field is due to the nucleus here. And we're going from whatever the radius r was to infinity. And we've already evaluated this integral, right? So what we're going to get is a 1 over 4 pi epsilon 0 E times 1 over infinity minus 1 over r. And if we say r is our atomic radius of 1 times 10 to the minus 10 meters, then we get this potential difference is going to be, and this, of course, this term is going to give us a 0. So we're going to get a 0 minus 1 over 4 pi epsilon 0 E over r. That's equal to a minus 9 times 10 to the 9th times 1.6 times 10 to the minus 19 coulombs divided by 1 times 10 to the minus 10 meters. And so we get a minus 14.4 volts. Which means a kinetic energy of, so delta U is E delta V. It's minus E delta V, so that's going to give us 2.3 times 10 to the minus 18 joules is the amount of energy the electron needed. Okay, so the electron, to get this kinetic energy, so to get this amount of kinetic energy, 2.3 times 10 to the minus 18 joules, the electron has to travel through a potential difference to get that. So we have delta K plus a minus E times delta V is 0. So K final is a minus E delta V. And so delta V is going to be K final over E. And that gives us 2.3 times 10 to the minus 18 joules divided by 1.6 times 10 to the minus 19 coulombs, or a plus 14.4 volts. So the electron must be accelerated through a potential difference of 14.4 volts. Well, now we can solve for the applied electric field, because that's just this potential difference over d, which is the mean free path, which is how far the electron gets to travel before it collides. So that's 14.4 volts divided by 5 times 10 to the negative 7 meters. And we get an electric field of approximately something like 2.9 times 10 to the 7 volts per meter. Now, experimentally, we found that the critical field was 3 times 10 to the 6th volts per meter. So it looks like we're off by a factor of something like 10. So is this model reasonable? Last time we were off by 10 to the 5th. This isn't bad, is it? Here's a situation where we made a lot of approximations. We could, how could we refine it? We could use statistics, because some electrons travel farther than one mean free path, and so the fraction that does would need a smaller field, and you only need a few of them to get this going. Not every collision has to ionize a molecule. We could do a better job of estimating the size of an atom or whatnot. So yes, this is pretty good. So let's think about how to test this model. It depends on the mean free path. So we would predict that if the air density is lower, the mean free path is longer, and that means we wouldn't need such a big field. So E critical should go down. So if we say density, if we take the air density is half as much, the mean free path is twice as big, and so E critical should be divided by 2. So that's something we can test experimentally. And guess what? That's actually what happens. So we lower the air density, the critical field goes down. We raise the air density, the electron can't travel as far, and so we need a bigger field. So it looks like this is a pretty good model, and we've put it all together. We have our invaders from outer space, our muons generated by high energy protons hitting the atmosphere, which travel fast enough that somehow they magically live long enough by the magic of special relativity, with time flowing more slowly in their reference frame, so they don't think they're aging as much. And they get down to close to the Earth, and all we need is one free electron, it turns out. If we can just get a muon to collide with one oxygen or nitrogen molecule near the surface of the Earth, we just need this one free electron, which is a gift of the muons, to start a chain reaction that produces more and more and more electrons. And when an energy calculation shows us that we are in the right ballpark from the observed field, and this model allows us to make a prediction that's testable by experiment, and we find that that actually confirms it or affirms the model. Now, one thing that might be amusing is just to calculate the drift speed of a free electron in a spark. If its final kinetic energy is about, we'll say it's a half mv squared, and that's about 2.3 times 10 to the minus 18 joules. If we solve for V, we get V final is about 2 times 10 to the 6th meters per second. So a V average would be about 1 times 10 to the 6th meters per second in a spark. And remember that in a wire in a circuit, we found drift speeds on the order of 10 to the minus 4 meters per second. So a spark is a very much more violent phenomenon. So thunderstorms are interesting. So how do we get the field? There's a lot of work on this, and it's pretty interesting, but in clouds, there's a lot of convection. There are air currents that are circulating around, and there's enough friction that in fact, just due to rubbing and contact, things do get ionized. And because of the way the air currents work, clouds often end up, or just because of fluctuations, clouds often end up polarized, so that they've got, say, negative charge on the bottom or positive on top. It can happen either way. This polarizes the Earth, which is wet and has lots of mobile ions in it. So the polarized cloud polarizes the Earth, and all we need is one free electron somewhere. Now, where's the field going to be biggest? Well, it's either going to be biggest near the cloud or near the Earth. Usually, I think in the slow-mo photos, you see lightning starting near a cloud. And so we have the same process. All we need is one muon and one free electron. And then we get a conducting path. And it can happen in pieces, right? I mean, you see lightning go a little bit jaggedy paths. And so we need to build up enough charge flows down here to make a charge concentration here, which then has a big enough field to make to have conduction this way and that way and that way. So, well, the clouds are discharging into each other. So cloud to cloud lightning, you're getting currents going from one cloud to another, or from one within a cloud. It's this charge separation within a cloud. So you're actually getting discharge where the charge separation is kind of being neutralized in the clouds. Lightning is very cool. So we are out of time and at an end here. I wanted to say thank you. You guys have been awesome. It's been a crazy rough semester and end of semester. You have hung in there. I know that some of you are living in situations which make it really rough to work well and to make it to classes, and you've done a great job. You've been amazing. So thank you for hanging in there. UNT really is resilient, and you're embodying that ideal. So I've really enjoyed this class. I'm been very sorry that I haven't been able to interact with you in person, but I'm glad for the interaction we've had here at the end. And thanks for hanging in there, working hard. You've learned a lot, and you've been wonderful.